Hey, good morning, guys. Welcome back to Introduction to Computer Networks at NTU. You know what? This is week 14 and episode 26. And today we got a lot to talk about, so sticking to the topic straight. So yesterday we ended introducing this property of distance vector routing called good news travel fast. Okay, today we're going to talk about the issue, okay, the downside of distance vector routing called the bad news travel slow. Okay, so much of the first hour today is going to be you and me back and forth going through quiz 46 to 48 to demonstrate bad news travel slow. And after that, Polly is going to introduce a mechanism called Poisson reverse that would try to eliminate some of the negative effects of bad news travel. So, okay, and we summarize link state versus distance vector, the two routing principles. Okay, so this is the first hour today, and in the second hour, starting today, we'll begin to introduce the real internet protocols that run based on these two principles, either link state or distance vector routing. And so in that part, the lecture is going to be more descriptive, which means not as many interaction as we walk through the quizzes. But in the second half, Polly will be also still taking some polls, so you get to express your opinions, okay, your preferences. So now, let's dig into bad news travel slow. As I mentioned yesterday, what we'll do starting today is starting with the quiz 46. All right. Let me go to the whiteboard mode so that I can interact with the whiteboard. So this is quiz 46. This network here is exactly the one we used yesterday to demonstrate good news travel fast. In that case, we see the link cost between X and Y is reduced. That's good news. And for bad news travel slow, you see the link cost is increased to 60. Super bad news, right? And what happened when the link cost changes this, if you recall the distance vector routing algorithm, it's an endless loop of 3 steps, isn't it? Collecting distance vectors from the neighbors, reapply the Bellman-4 equation, and then if there's something new discovered in the distance vector, propagate the distance vector further. Okay, but in that pseudocode, we thought that the only condition to trigger Bellman-4 computation is to receive a link state report, distance vector from neighboring nodes. But that's not the only condition. If you read the description closely, the slides closely, there's another condition that triggers the Bellman-4 computation, which is what? The link cost change. All right. So yesterday we demonstrated how good news will go fast. Today we'll try to do bad news travel slow. And so for quiz 46, what you're asked to do is to tell Y's table. So we'll apply the Bellman-4 equation and derive Y's table at T0. Now, this is going to be challenging for you guys to work on from scratch. So no worries. Polly is going to derive Y's table at T0 first. So that is saying this. Polly is going to tell Y's table after the link cost change. That is T0. Okay? And you guys will do this. Tell Y's table, okay, at T0. So that is, Polly telling X's table first. And here's the video showing how Y is derived. Table in Y is derived at T0.
Yeah, quiz 35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. Yeah, the xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that would be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from node y in order to find out, right? That is y's perspective. So that's in dy came from node y earlier. So dy y, then it's 0. And then, yeah, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz, to y. So dz to y. And that is in, distance vector of z came from node z earlier. Z to y, it says 1. So we put 1 here. Okay. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, node z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z.
Oops. Okay, guys, sorry, press the wrong button. And now you guys work on y at t0, which is interesting. Yeah, which is doing this over here. Okay, so let's go to the score space, channel W14, quiz 46. Yeah, guys, you see, the purpose of quiz 46 to 47 and 48 is so that you pick up doing the distance vector derivation. So you want to do it on your own. And we are not asking for fast responders for bonus, okay? So we'll just do this as it's just an exercise for you to prepare for the exam, for example, okay? So you have 10 minutes time. It should be abundant for everyone. And one of you guys might represent your team, and I'll put the solution on the score. But I ask all of you exercise and make sure that you learn how to do distance vector computation, okay? So 10 minutes, it's now 10:28, so we'll come back to check on your guys' solution at 10:38, all right? And let's start counting time. And guys, by the way, it's okay. If you make errors, that's perfectly fine because it's an opportunity to learn. And the whole point is such that you make sure that you clear all the misconceptions and so that you will do well in exam 3. All right? So let's see. Bing Wei, team 2. Think again. Think again, Bing Wei. Look at your DZX. For distance, YX, the other option. Yeah, DZX. What is the value there? So you have to look into your table. What is the current DZX? All right. So DXZ similarly. What is the current DXZ? Yeah, team 2, great job. Bing Wei, you've discovered, right? Very good. So it's a little bit interesting, isn't it? A little bit different from you thought. What's going on there? I believe that Bing Wei, as human beings like you and me, we see the distance from y to x should be 51. But you see that as a distance vector router at the time, the Bellman-4 computation is triggered. It's not quite. X to z is still 5, isn't it? That's the reason that when you are deriving distance vector routes, we use a table like this, because then you consider the current route based on what you have at the moment. Okay, so it's a local information algorithm, not only spatially but also temporally, guys. So let's see. Team 10, you're perfectly fine. Team 6, correct. And team 20, Kelvin. Yeah, you're in the same situation with team 2. So the DZX is not exactly 50. Tricky, isn't it? Okay, team 20. Team 14, similarly. Alan, Yeah, dzx is not 50. All right, Sherman. Yeah, good that you changed the derivation back to the Bellman-4 equations. Because this is the case, you see that the general algorithm, the notations or derivation you use for the algorithm course, because those algorithms are presented under the assumption that there's no route change. You're given a graph and you calculate the shortest path at that moment in time. And distance vector is actually very dynamic based on local information. And for some reason, you just need to use the Bellman-4 equation there. Okay, good. Team 15, very good. 17, all right. All right, good. And you know what? It's almost 37. It's also about the time I felt that it might take you guys to pick up what it is. Okay, so just team 20 and 14. All right, Kelvin and Ellen, reconsider your answer. And in case you're still a little bit confused, no worries. Here's Polly playing the video, deriving y's table at t0.
dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right, it should be 60, obviously, but this is as a human, you see the global topology, you know it's 60, but distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful, and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first. And then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y. But y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. Okay. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
All right, guys, did you see the issue? The issue is that when the link cost change happens, yeah, the table is still at the present time. What is the best route from z to x, which is 5. And y to z is 1, so z to x at this moment after the link cost change is 1 plus 5, 6. All right, so let's exercise more. and move on to quiz 47. So in 47, it's the same scenario, but you guys are asked to tell Z's table after first iteration, T1. All right, and that is this. After we get T0's table at X and Y, guys, now work on Z's table at T1. All right? And for this one, I think many of you get the point already, so let's reduce the computation time. How about 8 minutes, okay, this time, to work on quiz 47, all right? So let's go to the Discord space, channel quiz 47. Guys, you have 8 minutes, and let's start counting time. good. I see that all of you did well. Yeah, so just same, team 1. You see dx here to begin with. It should be the distance vector coming from x at t0. And t0 we already derived. It should be 0, 51, 50. Okay, so just, slightly imperfect, neglecting that. But otherwise, all good. And hey, Ricky comes to help. Great teamwork. All right, team 1, you're good. And so the next video is just Polly playing how she derives a z's table at T1. Just in case for the students not following up how the distance vector calculation is done.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. Right? And at T1, Z here can try to calculate dz because it now receives the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains 2 entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-4 equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, 2 possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these 2 entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 wings. And therefore, we update dz to 7, 1. Okay. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z. Yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finished calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay.
All right, good. This time I hit the right button. And so we move on to quiz 48. So let's just do one more iteration. And I'm asking you to derive y's table after the second iteration. That is this. We just finished developing z's table at T1, right? Let's propagate the table and try to develop y's table again, but at T2. All right. So let's go to the Discord space, channel quiz 48. And guys, for this one, let's reduce the time further because I see that some of the teams are getting familiar with the Bellman-4 equation computation. So let's just allocate 6 minutes. Okay, it's now 10:51. Oh, wait, 10:52. Let's come back to check the answer. 10:58. and let's start counting time. All right. Yeah, time is close, but I see that all of you so far have correctly answered quiz 48. So you guys are picking things up really well. So here's the final video, Polly deriving also Y's table at T2, and then explain how come in this case the bad news would travel 44 iterations until the whole network finds the true path, okay, to each other nodes.
Let me bring up the result. dyx, this value here, is gonna be 8. Let's look through it again. Okay, from y to x, y to destination x. Through neighbor x, neighbor z. Link cost 60, link cost 1. Link cost 60, link cost 1. The xx, 0. The zx, look up the table. Z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here, actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only $7 to go to x. And this is going to go on, in fact, because y here is going to announce dy also, to all the neighbors. And z is going to recalculate the dz. And guess what? And the next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cause to x. So until, in dz, the value becomes 50, 1, 0. Okay, and how many iterations would that be? Yeah, came all the way from 7 to 50, that will be 43 iteration, okay? And including the initial iteration, that will be what? 44 iteration, okay? Until, z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
All right, so you see bad news travels slow in distance vector, okay? And you know what? It's not a problem that's not solvable. In some cases, one can apply this mechanism called Poisson reverse. And here's the video introducing the idea of the Poisson reverse.
The problem here is, right after link cost change, when y is trying to recompute, the best route to x to z, particularly to x. Bellman-Ford algorithm says y needs to try, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, just to get from y to x. So together, total cost 60. Not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. So y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So z is going to send the packet back to y. And y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, until y discover, the real shortest path to x. So z here, being still under the impression that the best route is the one before the link change, needs to know about the link change. Poisson reverse is working this way. This is to help, preventing bad news travel slow. In Poisson reverse, y and x, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, all your shortest path routes to the other node along the link needs to be changed to infinite. That way it prevents y selecting z as the shortest distance to x.
So you see, yeah, the issue is that when the link cost changed, all the neighboring nodes of the two nodes adjacent to the link, they might be thinking that there's a best route through this link that the link cost has changed. And that's why leading to this trickling down effect that it requires multiple iterations to finally come to the true path, true optimum path. So therefore, the Poisson reversed, the idea is for the nodes, okay, adjacent to the link, having the link cost change, informing the neighbors. In case you're taking this link as the best path, definitely change, okay, your distance vector table, okay, to infinity. That's really, really bad, so we can quickly converge to what's true, okay. So no worries, it sounds a little bit abstract with just the idea. Here's an example showing how you apply Poisson reverse, okay, and it's a little bit long, 5 minutes. Be patient.
Let's use the same example to illustrate how Poisson reverse works. So taking one step back before we have the link cost change. Now Z here will discover a shortest path to X this way, Z, Y, X. So shortest distance from Z to X is 5, and the next hop router is Y. Now, link XY here, the cost changes from 4 to 60. X, Y, these two routers being connected to the link will be able to discover the link cost change, but Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, when we're calculating the shortest distance from Y to X, we ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay? A funny value for the shortest distance from Y to X, which we see from the network after link cost change. There's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay, Z from keep telling Y this is the shortest distance. So Z tells Y instead, okay, the distance to X is not 5, instead being infinite. Okay. And that is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. Okay. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if Y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination, okay, set this entry here in Y's table to infinite. With now the Zx being changed to infinite, the way we calculate dy in iteration t0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6, okay, but now let's see how it's going to look like. From y to x, okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx, dxx, dzx. Set up table, xx 0, zx infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1, 50 and 1. The xx and the yx, the xx, the yx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wins. And you see here, from Z to X, yeah, we're taking just this link, ZX, as a direct path to destination X. Quite different, isn't it? So we update DZ, and DZ is going to go to the neighboring nodes. Okay, and so Y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes. 60 and 1 are the link cost. The XX, 0. The ZX, ZX, entry value being 50. So 51 compared to 60, 51 wins. So to go from Y to X, now the shortest distance is, this path. And in fact, at this point in time, so let's update the distance vector for Y. At this point in time, the network converged to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
All right, so that's the idea of Poisson reverse. And you know what? It's now 11:08. It's not going to be enough time for us to play the summary video, okay? And after the summary video, we'll also take a poll, and that's also going to take some time. So I propose that we take a break now for 10 minutes, and it's now 11:08, and we'll resume the lecture at 11:18, okay? Welcome back. Let's continue and summarize link state and distance vector routing. And Polly is going to take a poll at the end of the video asking you which of the two routing principles you prefer now.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. dV is the distance vector. Let's compare the message complexity first. If you recall in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links, and there are E of them, and there are N nodes. Each will be generating these link state reports. Therefore, overall cost N E. In the worst case, in case the network is very well connected, the E here is about the scale of N squared. Okay, so overall, the cost can go as high as N cube. So link state message complexity, not good at all. Distance vector, on the other hand, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. So in terms of message complexity, dV is slightly better. Now, the second metric, the speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being N squared. There's some optimizations one can apply that takes you to N log N time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much in the scale of the diameter of the network. But that is actually in the ideal situation. What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, the packets will be looping from router to router. So in distance vector, the convergence time is a little bit hard to predict. It really depends on the situation. On the other hand, link state very predictable. I would say in terms of predictability, link state wins over distance vector. But under normal situation, distance vector's convergence time is indeed the diameter of the network. There's not many hops. Even for a large network, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Things like that. In link state routing, during the phase that router is malfunctioning, yes, the neighboring nodes will be advertising the wrong link state reports. And each router will be calculating the shortest distance based on the wrong link state report. But once the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, if a router is malfunctioning and reporting, for example, a short link cost to a particular neighbor, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DB and then pass the incorrect information further. Each node's table is going to be used by the other. Each node's distance vector is going to be used by others. This error is going to propagate out throughout the network, and it might take a long time for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, link state here is still winning by a head, by a neck.
All right, now you know better link state and distance vector routing. There's a pop-up poll on the live chat. Polly asked, knowing LS and DV better now, which one do you like better? If there's a reason or two, let us know. All right, so link state or distance vector? I know. It's hard, right? Link state, not that scalable, but distance vector, not that robust, not that predictable. Between the two, which one would you pick? Okay, guys, take your time. But you know what? Maybe we should probably move on. And the next topic, in fact, the rest of the topics will be talking about the internet protocols. In the first video, Polly is going to explain first why there's need of creating a hierarchy in the internet routers. Because for the very simple reason, internet is huge. There are so many routers. And if we use link state routing, to connect all the routers, you see that there's a scalability issue, right? Computation time n square, the broadcast messages n square, and what? Each router needs to maintain the network topology, so the entire topology of the internet n square, that is not going to be scalable. So there's no way you run a link state routing algorithm on the entire internet. And you see also that in distance vector, it's not exactly robust. Whenever there's link change, yeah, you get this, unpredictability. You're not quite sure when the best routes will converge. Okay, therefore, what we do there, okay, on the internet is this: to try to group a bunch of routers together under the same management together, and we call this an administrative system or an autonomous system, okay, AS. So within an autonomous system, the network admin can pick and choose whichever routing protocols to run for the network. And then between the autonomous systems, we run another protocol at the higher level, and everyone will be running the same routing algorithm. All right. So in this video, you'll hear in the first part. Oops. Oh wow. Okay, I get an error message saying OBS. Okay, it's reconnected. All right. So I'm actually not quite sure what's happening now. I guess that there's a sort of a brokerage there, okay, earlier. Sorry about that. That is not something that I can control, so obviously. But yeah, good to see that some of you typing up your opinion about link state versus distance vector. All right. But let me move on to describe autonomous system, the first video. So first, in the first video, you'll hear Polly explaining why there needs to be a hierarchy, and we need to form, okay, this term, this autonomous system. So I'll be introducing in the second part of the video the autonomous system, the term. Okay, so let me play the video. It's a little bit long, 5 and almost 6 minutes. And after we play the video, we'll come back to check on the poll. All right.
Next, we'll be talking about two routing protocols that are actually running on the internet. First is called the OSPF, and it's based on the first principle, the link state routing, the one implements the Dijkstra algorithm. The second, BGP, is then based on the other routing principle, the distance vector routing. Well, to be exact, BGP is not just distance vector routing. It's an extension of distance vector routing. It's the path vector routing protocol. And just to tell a little bit more, okay, OSPF is the routing protocol that runs predominantly within a network, a local network. While BGP, this other one, very, very critical, very, very important, is running on all these backbone routers, okay, all over the internet. Let me take you back to the way we describe these routing algorithms. In that, I introduced the graph abstraction, right? So routers are considered nodes and links considered edges. And therefore, we have a graph where we have edges interconnecting the nodes. So all these nodes, very simple, and considered equal. And the graph there you see, the network is completely flat. There's no clear hierarchy. But on the internet, it's so not the case. Okay? So until now, the way we're introducing these routing algorithms is actually very idealized. Okay? Taking a link state routing and put it down to the internet and consider every router as a node, that's not going to scale. Even taking a distance vector routing algorithm, which is already more scalable than link state, if we just put it into the network and having all the routers on the internet implementing distance vector, it will still not scale. Why? Take a look at this. How many possible destinations we might have on the internet if the internet is completely flat? If we draw the graph of the internet, okay, there's going to be how many? Yeah, these many destinations. Therefore, in each of these distance vector routers, in order to store the shortest distance to each of these destinations, in order to store the predecessor, okay, to each of these destinations, how much memory is required? Well, let's say we use 1 byte to represent the shortest distance, 1 byte to represent the predecessor. We'll need 2 bytes, okay, for each destination. And there are these many destinations. If my calculation is correct, this is probably something at the scale of about 8 gigabyte. Yeah, or something like, close to gigabyte. Wow, this is a lot of memory, right? Just to store routing information. And not to mention that we have forwarding tables and all these other things that might be necessary. Yeah, not gonna work very well, right? And if you think about this, hey, this is IPv4 address space. What about IPv6? Ouch, okay, you don't wanna go there. Okay, so even if we use a more scalable routing algorithm, distance vector, okay, consider it working on the internet, not gonna scale. Okay, we cannot be storing all destinations. And you know what? Each of these distance vector routers also send distance vectors to the neighboring nodes, and neighboring nodes sending to neighboring nodes. Okay, these distance vector exchange, it's also going to swap the link, right? Because each of them is this big. You need to send really, really long messages to make sure that the entire 8 gigabyte of this very basic distance vector table gets to the neighbors. Okay. Ouch, and ouches probably. You see, it's not going to work if we treat all routers the same and run just one routing algorithm throughout the internet. It's just not going to scale. Okay? So what we do really on the internet is this. We'll group the routers that are nearby belonging to one organization together as a system, as a local area network. So these are other routers nearby belonging to another organization, another system. Now each of these systems can work independently. The network admin hired by the organizations could decide independently, autonomously, okay, what routing algorithms they would like. So routers being interconnected in this system can be configured running link state routing. So all the routers running the Dijkstra algorithms. This other system here, okay, the system admin can decide maybe distance vector routing is better, okay, more scalable, better. So all routers here then will be running the distance vector routing. Okay. So systems. What happened on the internet is also this. Each system, the network admin is going to configure, okay, 1 or 2 routers and make them the delegate routers. These delegate routers, okay, at the higher level will interconnect. Okay, so this system's delegate routers and this system's delegate routers, they might interconnect. Okay? And there could be lots of these systems around all over the internet. Their delegate routers will interconnect at the higher level in the backbone of the internet. And all these routers in the backbone is going to run one routing algorithm. Okay, so distance vector or link state. Okay. Well, to just tell you ahead of time, okay, for internet, the backbone routers run something that's more like the distance vector because it's more scalable because we don't know how many systems eventually the internet will grow into. Okay. So you see 2 levels of hierarchy. Yeah, there's backbone network, and then each delegate router there associated with it is a local area network. Okay, so internet, again you see here, in terms of routing, is also a network of networks, a network of these autonomous systems.
All right, so internet, in terms of routing, is also a network of networks. It's a network of autonomous systems, all right? We'll come back to the internet routing shortly after we check on the polls. So here's answer from Team 1, Sam says, I consider robustness more important. As a result, Sam here chooses link state. Even though distance vector is more scalable, I don't think a user would like to see his/her packets being able to, frequently, not being able to reach the destination frequently. Yeah, that's a good point because internet is definitely dynamic. So when it comes to dynamics, link state, although not as scalable, handles dynamically a little bit more timely. But distance vector, in the worst case, it can be horrible. Okay. And let's see, Ivan here, distance vector is more economical, but I think link state is much easier to implement and more expectable. Good. I think I would choose distance vector for its saving resource better. Okay, so very good. Ivan here is saying that there's pros and cons, but Ivan here would still prefer distance vector because of the scalability issue. Okay, so far one link state, one distance vector. Kelvin here chooses link state. It reacts to change faster. Okay, so I have now 2 link states. Jaden here is, I lean towards link state for its robustness and predictability. It avoids count to infinity problem. Yeah, that sounds really bad, right? So 3 link states. Okay, Caesar here prefers link state as well because it's faster and easier to calculate to the shortest path. Despite the resources required. So it seems, right, there's no one solution that's perfect. It's either that you want robustness or you get scalability. Distance vector in a way is a cheaper solution, but less robust. Okay, so link state seems to be edging out here. Oh, good. Sherman says distance vector. The network cannot be walked through exhaustively. It's hard to apply such method to a big memory. Exactly. In some cases, there's just not enough resource for link state. So in that case, Sherman prefers distance vector. It's well justified. Yuhan here says, I prefer link states fast to converge and robust to changes. Yeah. And you see, delay these days are a very important user experience index. And robustness, reliability is also an important user experience index. And Stanley prefer link state because even if distance vector is scalable, it's more to avoid any problem and be robust. Yeah, so Stanley here is saying that, hey, I would prefer reliability over cost, right? Bing Wei also likes link state. Oh, I think link state is, taking a tremendous lead, which is quite opposite of the poll we took when Polly first overviewed the 2 routing principles. Remember, distance vector being local and link state being global. At the time, I believe that you guys prefer distance vector more. So Ricky here prefers link state because it gives optimum path and there's no convergence issue, right? Yanjun prefer distance vector. Okay, yeah, scalability is also important. And if internet is huge, one is very concerned, right? How these link state reports are going to reach out to everyone. That's a potential headache as well. I prefer link state, Devin says, because it is more robust and it converges faster. Indeed. Josephine also prefers link state because it lets each router see the full network map. Yeah, because it's just more straightforward and you feel that you have more control. I prefer link state more. Iris, yeah, it ensures stability more. Exactly. And Anthony, distance vector. It's easier to implement. Yeah, you know what, Anthony, it is, because you don't have to implement this data structure to maintain the network topology. That is a lot of work itself. Okay. Good, but from what I see from the poll second time, yeah, the preference is now leaning towards link state. Yeah, but hey, good timing here, checking the poll. You see, the second video I'm going to play is to say this. Internet routing is hierarchical. We actually use a combination of link state and distance vector. Okay, so for within autonomous system, it's very often we see administrators choosing a link state based routing protocol because it's smaller in scale. But at the higher level, involving the entire network, connecting many autonomous systems. You see that the internet is still growing, and there are more autonomous systems. Okay, and so at that level, we actually use a distance vector routing. It's called BGP that we will talk about next week. So on the internet, we use intra-AS routing, that is routing running within AS, and inter-AS routing, that is a routing mechanism running across inter-ASs. So in this video, the first part probably will introduce these two terms, intra-AS and inter-AS. And intra-AS runs within an autonomous system among all the routers within the autonomous system. You see that with each autonomous system, there's going to be a delegate router. If you recall the video we just played, there's a delegate router, or we call in this video now the gateway router. These delegate routers or gateway routers, then they will run the distance vector, another routing protocol, and that routing protocol is just one, okay, which is called BGP. But within an AS, the intra-AS, the system admin, the network admin can choose, like you guys, some prefer link state, some prefer distance vector. Choose whichever you prefer, depending on the property of your network, depending on what your users prefer. Okay, so that's the next video, 4 minutes and 20 seconds.
Once again, on the internet, we aggregate the routers in a region and call it the autonomous system, an AS. Or sometimes we also call it a domain. So the internet is a network of ASs, a network of domains. The routing protocol within the AS, the network admin configuring all the routers running, is called the intra-AS routing. So you see here, it's the routing protocol running among all the hosts and routers in the same AS. All routers in the same AS will need to run the same intra-AS protocol. Now, routers belonging to different ASs can then run different intra-AS protocol. That is an independent, autonomous choice of the network admins individually. Now, each AS will also pick powerful routers, usually sitting at the border of the AS. These powerful routers, I call them the delegate routers earlier. Yeah, here you see a more formal way of calling them are the gateway routers. So gateway is what? The doorway. Yeah, the router sitting at the border of these AS, connecting to another AS. Okay, so gateway routers, powerful delegate routers, will be sitting at the edge, the border, of its own AS, and have links both within towards routers within the AS and links to routers in other AS. And therefore, this routing protocol, running in the backbone of the internet, is called the inter-AS routing. Okay, so that is the routing protocol that's running across the gateway routers. So this is the routing, working among the ASs, and the gateway router there will be doing the inter-AS routing computation. And on the slide here, you see an example of ASs and how ASs interconnect. So we do have 3 ASs, 1 here, 2 here, and 3 here. You see individual routers interconnected within one AS. Okay, so there are 3 here for AS2 and 3 more here for AS3. Now, AS1, 2, 3 each could run its own intra-AS routing, but you see 1B and 1C, both of these routers have links internally as well as externally. So 1B and 1C are the gateway routers. So these 2 gateway routers. Just like 2A for AS2 is one of the gateway routers. 3A for AS3 is one of the gateway routers. And inter-AS routing is running in between. 1B, 2A, 1C, 3A, and so on and so forth. Now, the focus of this slide is to talk about how would the forwarding table look like when we have 2 levels of routing running on the internet. Now, let me show you an example here. 1D is one of the routers existing on the internet. What's going to happen there is the forwarding table is not going to be just contributed from the intra-AS routing algorithm. It would also be contributed from the inter-AS routing algorithm. As you see earlier, in order to pass data from one router to another router that's far away, not within the region, right? You need intra-AS routing to find the gateway router. And you also need the gateway router to find hey, where's the destination gateway router? All right, so you do need inter-AS routing algorithm telling each node where to pass data further. Just like you need intra-AS routing there telling you how to reach another router within the AS. So forwarding table here will be configured by both intra and inter-AS routing algorithm. The intra-AS routing determines the entries for destinations within the AS, within AS. And inter-AS determines entry for the external destinations. To be precise, the inter-AS determines which gateway, which router here you should be passing the data to. But intra-AS will also be telling 1D here to go to that particular gateway router, what is the right way. So you see here, interplay of inter-AS and intra-AS routing for packets going outside of the AS.
All right, so you see towards the end of the video, the forwarding table will be a little bit more complicated on the internet. There'll be entries that are for intra-AS routes, and there'll be also entries for inter-AS routes. So if the destination is outside the AS, they'll be going through some other routes. All right, so forwarding table gets complicated. And you see that on the live chat, there's a question from Henderson. Is it possible for one router to belong to two ASs? You know what? In practice, I've never seen a router belonging to two ASs. What happened more is that each router will assign a few gateway routers. And between ASs, the gateway routers will connect directly. And that's how the routers, especially the higher level routers, are connected. So no two ASs share one router, because you can imagine all these routers need to be administered by someone. And someone needs to be in charge, or someone needs to be responsible. So each router will belong to their ASs. But ASs need to connect. So how they connect is that the gateway routers connect to each other. And sometimes you will see multiple gateways connecting to each other for fault tolerance. Okay, good. I hope that addressed your question, Henderson. And we have one more video introducing autonomous system. So you see that, hey, if it's just intra-AS, a bunch of routers, if you run a link state or distance vector, we now know how link state and distance vector works. So it's straightforward imagining how routing is like, right, within an AS. How does routing runs inter-AS? How does it work? So the key idea is this. For the destination AS there, announcing their existence, by sending messages, by sending reachability information to the neighboring ASs, to the gateway routers of the neighboring ASs. And these gateway routers of the neighboring ASs will further propagate that information. All right, sounds familiar? Yeah, if you're thinking distance vector, yeah, that's very similar. Okay, you initialize a distance vector table, and then you propagate that further. So that's the idea of how internet does inter-AS routing. So this is what the next video is about, 4 minutes.
To make sure the interplay of the intra-AS and inter-AS routing is more clear, let's take a step back. Look at AS1 here, 1A, 1B, 1C, and 1D. So these routers within AS would run the intra-AS routing. Therefore, they would know the shortest path going to each other. No problem. Now, at a higher level, at the inter-AS routing level, so we have these gateway routers. 1C and 1B are the gateway routers of AS1. 3A, obviously a gateway router for AS3. But you see here, 3B having also connectivity to outside to another AS. 3B is also a gateway router for AS3. Similarly, 2A, 2B, 2C all have links to outside to other ASs. So they are also gateway routers. So these gateway routers at the higher level will be running the inter-AS routing, so that's another routing protocol, and they will all be running the same routing protocol. They will exchange information to each other using the link state or the distance vector routing to come up with the shortest path. But this time, the shortest path is what? Oh, if I want to go from AS1 to AS2, the shortest path is to go directly from AS1 to AS2. Now, if there is another AS here, AS4, for example, okay, then the shortest path might be to go from AS1, AS2, and then AS4. So these gateway routers will maintain shortest path, but shortest path in terms of, what is the next AS to the destination AS? What is the next AS to the destination network? Okay. So we might have another AS here, AS5. Then the shortest path from AS1 will be what? AS1, AS3, and then AS5. Okay. With those said, we may now walk through the scenario here. Let's suppose a router in AS1, say 1D, and it's got packets to go outside of the AS. Let's say AS5 here. Okay. Now, we see the shortest AS path will be the what? A1, AS3, and then AS5. And this information will be available here at the gateway router, 1C, 1B, 3A, 3B. But 1D here as an internal router. So this router here, we'll have actually trouble judging, right? Among the two gateway routers, 1C and 1B, which one of these 1D should be passing the packets to, so that these gateway routers will be able to pass further to the neighboring router along the shortest path to the destination. This is also saying, even though these routers are internal, they participate in intra-AS routing. They do not participate in inter-AS routing, but they need still to know the shortest AS path to these destination ASs out in the world. Okay. So 1D, 1A don't do inter-AS routing, but they still need to know the inter-AS path. Okay. So they must learn the inter-AS path, which is to know for each destination AS, is it AS2 or AS3 being the next hop AS to the destination AS? And this is essentially the inter-AS routes. And how? Okay, how does 1D and 1A learn? Well, you know what? 1C and 1B do participate in inter-AS routing. So 1C and 1B thereafter, inter-AS routing will then propagate these AS path information to all routers inside AS1. And so propagation of the AS path, just like computation of the inter-AS path, would also be part of the job of the inter-AS routing.
All right, so now you get a general idea of how internet routing works in two levels of hierarchy. Now we focus on talking about intra-AS routing. That is the straightforward part. Okay. So the first video talks about the variety of routing protocols one might use for within an AS. So pay attention to these varieties. Polly is going to ask a pop-up quiz, at the end of the video.
The first big category is the intra-AS routing. So this is the routing protocol runs on the routers within an AS. It's also known as the interior gateway protocols, IGP. And here, interior gateway, not to be mistaken with the gateway routers. So gateway routers are the routers sitting at the border of an AS, having connectivity to other ASs. So gateway router there are to interconnect ASs. But interior gateways are completely internal. Okay? And then running on these internal routers within an AS, we have three very well-known protocols. RIP here, not really standing for resting in peace, it's actually Routing Information Protocol. Okay? But if it adds the impression, RIP, this protocol is also the oldest implementation of an intra-AS routing. It came with the Berkeley's BSD distribution in the 1980s, late 80s. And it's based on this principle, distance vector routing. Okay? Yeah, nowadays I'm not quite sure. I don't know if any network admins is running RIP for their intra-AS. Okay? But this other one, OSPF, short for Open, Shortest Path First Routing Protocol, this one on the other hand is very popular. Okay? So open here stands for open source. Okay? RIP is also open source as it came with the BSD. So it runs also the shortest path first routing. Yeah, you guessed. Yeah, it's the Dijkstra shortest path algorithm that's running, and therefore it's based on the link state routing principle. And to make sure that we credit the right people, OSPF is actually based on ISIS. It's another routing protocol that was designed maybe 3 decades ago, okay, by early researchers for distributed system research as well as these multiprocessor system research. So in those paradigms, having multiprocessors, if you want to pass the messages around, and these processors are actually forming an interconnected network, you also need to find a path to go from one processor to another processor. Okay, so at the time, okay, those researchers, those computer scientists, have designed ISIS for the purpose. Okay, OSPF for internet, which is also a distributed system. It's just that it's very loosely connected distributed system. Yeah, borrow much of the design principles from ISIS. Third one is called the IGRP, Interior Gateway Routing Protocol. Now, this one is completely closed. It's Cisco proprietary. Okay. It came with these Cisco routers, but it only is maintained until 2016, okay, and obsolete afterwards. The reason for that is because Cisco is also beginning to embrace the idea of doing software-defined networking, okay. So if you recall, in software-defined networking, routing is all done in the remote controller on the powerful machines. So the routers there, okay, in SDN, pretty much are doing what? Generalized forwarding, okay, and allowing the flow table being installed, and that's pretty much all, okay. There's no need of running routing algorithms on individual routers. Okay, so starting from 2016, Cisco stopped maintaining IDRIP because there's really no need, very little need of doing routings inside the router.
All right, now the pop-up quiz today. So I asked in the live channel, what was the, okay, here it is. Pop-up quiz number 1. It's not a poll, it's a quiz, okay? If you pay attention to the video we just played. Is OSPF a link state or distance vector routing protocol? Yeah, Henderson, Jaden, Yuhan, Kelvin, Sam, Sherman, Ivan, Anthony, Yanjun, Stanley, Ricky, David. Yes, you guys are all correct. And I guess the name, open shortest path first. Okay, the shortest path probably gives it away because Dijkstra algorithm is exactly calculating the shortest path. All right, same for Bingwei. Very good. And now we come to talk about OSPF more because among these options, OSPF seems to be the most popular one till today. And the video is a little bit long, 6.5 minutes, because OSPF is essentially link state routing, but with quite a bit of extensions. And the 2 extensions probably find worthwhile mentioning, discussing more are, first, you see, link state routing is based on information of the entire network. So you need to collect information about the network topology. If there's any error, or if there's bug, or if there are malicious attackers trying to manipulate the network topology, then you might end up having a network that data not necessarily going to the destination they're supposed to go. So one can create black holes, or hey, one can easily pull a man-in-the-middle attack. So one of the very important extension of link state routing that's in OSPF is that the exchange of these link state reports are all secure. So it's a very important option. The second is that as we discussed, intra-AS, it's the network within a management, within an administration. That's usually a smaller network. But you see that many of the smaller networks are growing big, right? The use of internet demand is rising, okay? So one can imagine these ASs will grow gradually. And so the number of routers within an AS can also expand. So to some degree, some organizations might need a certain hierarchy because a flat link state routing does not scale when the size of the network grows. So a very important in OSPF is that it allows us to create two levels of hierarchy using OSPF. And the idea is similar to how internet sets apart intra-AS and inter-AS routing. So within intra-AS, one creates two levels of hierarchy, but at both levels, OSPF at the lower level and OSPF as well at the higher level. Okay, so two very important extensions. Pay attention and see if you can get it. In case one day you need to administer a network, you will know what to choose. Okay, so 6.5 minutes.
Yeah, let's speak a bit more about the most popular routing protocol here in the intra-AS category, the OSPF. Open here stands for, the protocol is open source. Second, the SPF stands for the routing protocol is based on the link state principle. So we do distribute the link state reports all over the network. Therefore, each router will be able to reconstruct the global network topology. From there, then we call the Dijkstra algorithm to compute the shortest path. Be a bit careful though, these routers sending these link state reports, okay, they'll be sending these reports in OSPF message. These OSPF messages are native IP packets, meaning the message itself, and then we append the IP packet header, and that's all. Okay, there's no TCP, UDP, or application layer header on top of that. Yeah, inside these link state advertisements, it's going to contain, hey, who the neighbors are for this router. Also, the cost of the link leading to connecting to these neighboring routers. Again, ISIS routing, this is the predecessor of OSPF designed by the early distributed system researchers. Now, what we haven't mentioned much yet are these. So these are the advanced features of OSPF. First of all, okay, these OSPF messages, very important link state reports, okay, they can be sent through a secure channel such that the receiver of these link state reports can authenticate, okay, the sources of the sender, therefore preventing malicious attacks. Okay, so yeah, if people can just send these link state reports around, okay, with no security check, one can easily inject a false route, okay, into the system. Second feature is this. One can actually exploit multiple same cost paths. Okay, so in case we come up with the topology such that the Dijkstra give us same cost paths and there are multiple of them, we could actually send data over these multiple same cost paths, okay, which is nice, okay, sometimes. For each link, the metric for the link cost, okay, can be defined also differently for different type of services. Okay, for example, if we are trying to serve best effort traffic, meaning traffic does not require timely delivery, okay, so the receiver can wait longer, then the cost of a satellite link, which the delay is longer, can be set lower, right? Because you would then prefer using the satellite link if the data does not require timely delivery. On the other hand, okay, if the data is real time, okay, then set the satellite link costs high. Therefore, we avoid choosing satellite link along the path to deliver the real-time data. Okay. And oh yeah, it allows also, OSPF allows also integration of the unicast and multicast. Now, if you recall in Dijkstra algorithm, in the end of the algorithm, what we ended up generating is from the source, from the router doing the computation, a shortest path tree. That is also saying that from that source, we could also send a copy of the packet along that tree to all the receiver in the network. So that is also a what? A very efficient flooding tree. Okay, that is a efficient multicast tree. So what multicast meant here is to send from one source to multiple receivers. Okay, so that Dijkstra shortest path tree is also a multicast tree. So from that shortest path tree, we could do unicast, sending from one source to one destination. One can, of course, exploit that to send from one source to multiple destinations. And in the meantime, guaranteeing that it's also the shortest multicast tree. Okay, so multicast OSPF, MOSPF, is a very nice and easy extension of OSPF. Oh, by the way, one can also configure OSPF to run in hierarchy, okay, such as this one here I'm illustrating. So you see, there are two levels of hierarchy here, at the lower level, area 1, area 2, and area 3. Okay. Inside each area, we could be running an OSPF, and all these internal routers within an area runs the same OSPF. It requires the same metric, link cost. And then at the higher level, you see, okay, in the backbone of this local area network, in the backbone of this AS, we could have also multiple routers configured. So these are called the backbone routers in general. Okay. Some of these backbone routers might be at the border, okay, of the AS. They are also the boundary routers. Some of these backbone routers, okay, are also, okay, the manager of the areas. Okay, so this guy here and here and here are the area border routers. Okay, so the area border routers, boundary routers, as well as the other backbone routers together form the backbone, and they will together run also OSPF, but that is independent of the OSPF running inside each of these areas. So this slide is pretty much repeating what I was just saying. In the example, we do have two levels of hierarchy. Okay, so at the lower level, we have these local areas, and at the higher level, the backbone. Inside each local area, the link state advertisements will only travel within the area. Okay? The link advertisements for the backbone network will be traveling only within the backbone. And each node, okay, in each area is going to know the entire area's topology. And the node inside an area will only know the direction, okay, to the border area routers in case the destination is outside, okay, of the area. So these area border routers, okay, will summarize the distance to the destinations inside its own area and advertise to the other area border routers. Okay, so that's how the area border routers discover each other at the higher level. Okay, and those advertisements will be shared by also the backbone routers and the boundary router.
All right, and that's all the content we have, because next is to start talking about BGP, and the time remaining today is not going to be long enough for even the first video. Okay, so with that said, thank you for your participation to the poll and the questions today, and I'll see you next week. Okay, and by the way, that will be week 15, the last week of lecture. All right. We're almost there. The summer break is coming. Good. So, bye. I see you next week. Okay, bye. Bye, guys. All right. See you next week.